Welcome to The Explainer. Today, we're going to pull back the curtain on the foundational principles of computer architecture. These aren't just abstract theories. They're the big ideas that give you the framework to really understand how computers work, and, let's be honest, to absolutely ace those tough exam questions. So, let's get right into it.
I mean, it really does seem like magic, doesn't it? You write one little line of code, and somehow billions of tiny switches flip in perfect sync. Well, it's not magic. It's actually a series of incredibly brilliant ideas that form a kind of bridge between the software you write and the silicon that runs it. We're going to unpack these ideas and give you that essential big picture view. Okay, our first great idea is abstraction. Honestly, this is the secret sauce that lets us build systems that are mind-bogglingly complex without our heads exploding. The whole trick is creating layers, where each layer only needs to worry about talking to the one right above it and the one right below it, hiding all the messy details. You might have heard this famous saying before, and it perfectly captures what we're talking about. Just like a stack of turtles, our entire digital world is a stack of these abstractions. Each layer rests on the one below, completely oblivious to the complex mechanics that are holding it up. So, what does this stack look like in the real world? Well, let's trace the journey. It all starts with a simple, human-readable idea, maybe a swap function you'd write in a C. A compiler then takes that and translates it into a much simpler language the processor can understand, like MIPS or Ledge8 assembly, which you'll definitely see in your courses. Then an assembler turns that into the raw binary, the ones and zeros of machine code. And finally, those electrical signals, those ones and zeros, physically control the logic gates and transistors. You've just gone from a pure idea to a physical action.
Now, the thing that holds this entire stack together, the absolute critical link, is the instruction set architecture, or ISA. You should really think of it as a formal contract between the software and the hardware. It spells out exactly what commands the software is allowed to give and what the hardware promises it can do. It's probably the most important abstraction in all of computing.
All right, let's move on to our second great idea. This one tackles one of the biggest bottlenecks in all of computing, the huge speed gap between the processor and the main memory it needs to do its job. Yeah, think about it like this. Your processor is a Ferrari, just revving its engine, ready to process data at incredible speeds. But it's stuck waiting for that data to show up from main memory, which, in comparison, is chugging along like a school bus. This massive, frustrating delay is what we call the memory wall.
To really get a feel for how big this problem is, let's use an analogy. Imagine that getting a piece of data from a register right there on the CPU takes 1 minute. Okay, getting it from the superfast L1 cache? That'd take about 5 minutes. But asking for it from main RAM? You'd be waiting for hours. And pulling it from a hard disk? You might as well pack a lunch for a trip to Pluto, because that could take years. The difference is just staggering.
So how in the world do we get around this? Well, we build a memory hierarchy, and it works because of a principle called locality. Turns out, programs aren't random. They tend to reuse stuff. Temporal locality is the idea that if you use a piece of data now, you're probably going to use it again very soon. And spatial locality means if you access some data, you're very likely to need its next-door neighbors soon after. So we just keep the important stuff in smaller, faster caches right next to the processor to hide that huge delay.
This idea of caching is so incredibly powerful that we even use it on memory addresses themselves. See, your program thinks in virtual addresses, but the hardware needs to know the actual physical address in RAM. To make that translation super fast, we use another special little cache called a translation look-aside buffer, or TLB. It's basically a cache for address translations, and it's what makes the entire concept of virtual memory fast enough to actually be practical. For decades, the game was simple. Just make single processors faster. But we've slammed into some hard physical limits with speed and power consumption. So the main way we get more performance now is through our third great idea, parallelism. The new game is, let's just do more things at the same time.
And you know, parallelism isn't just one thing. It comes in a lot of different flavors. We can do the same math on a bunch of different numbers all at once. We can run totally different programs on different processor cores. Or, and this is a really central concept for your course, we can use what's called hardware-software code design to build our own custom parallel hardware for very specific, slow tasks.
Let's just zoom in on one of those flavors for a second. Data-level parallelism, or SIMD. Instead of a normal add instruction that adds 2 numbers, a packed add instruction might add 4 pairs of numbers, or 8, or even 16, all in a single clock cycle. For anything involving graphics or heavy-duty science, this is just a massive, massive speedup.
Okay, so let's connect this to HW/SW code design, which is a huge topic for your exams. Here's the workflow. Let's say you're using a Zynq chip. It's got a regular CPU and also reprogrammable hardware called an FPGA all on the same die. First, you find the one function in your software that's super slow, the hotspot. Then you use a tool to automatically turn that C code into a hardware design. You integrate that new hardware block and boom, the main program runs on the CPU, but whenever it gets to that slow part, it just offloads it to your brand new, custom-built, high-speed hardware accelerator.
So, we've got all these fantastic ideas: abstraction, hierarchy, parallelism. But how does it all fit together? Well, our final great idea is understanding performance itself, which is always, and I mean always, an art of the trade-off.
When it comes right down to it, the performance of any program boils down to this one single equation. If you want to make a program run faster, you have 3 knobs you can turn, and that's it. You can reduce the number of instructions the compiler spits out. You can design the hardware to be more efficient so it takes fewer clock cycles per instruction, that's your CPI, or you can just make the clock tick faster. Every single optimization you can think of is just trying to improve one of these 3 things.
And this table here shows a perfect classic exam-style problem. You're often asked to compare 2 different ways of doing something, like a hardware sorter built on an FPGA versus a software sorter written in assembly. The hardware is going to be way faster because it's parallel, but it's totally inflexible. It only does one thing. The software is slower? Sure, but you can change the algorithm with a few keystrokes. This is the trade-off, right? Speed versus flexibility versus cost. There is no single best choice. There's only the best choice for the specific problem you're trying to solve.
And of course, anytime we start talking about parallelism, we have to talk about Amdahl's law. It's a really simple but incredibly profound rule. Your total speedup is always limited by the part of your program that can't be split up, the part that has to run sequentially. If even just 10% of your program is serial, the absolute fastest you can ever make it is 10 times faster, even if you had 1 million processors. So what's the big takeaway here? The main thing to realize is that computer architecture isn't just about memorizing facts and figures. It's about understanding a powerful toolbox of ideas: abstraction, hierarchy, parallelism, and performance trade-offs. The true art of engineering is knowing which tool to pull out of the box and how to balance them to crack the problem in front of you. And as we move into a future that's all about parallelism and custom hardware, getting a solid grip on these fundamentals is more important than it's ever been.